Hi. So for today, we are going to continue our discussion on Chapter 5, Electromagnetic Induction, and we're going to enter the topic on Faraday's Law. Okay, so we'll do a bit of Faraday. We'll do mostly Faraday's Law in this recording, and in the future recording, we're going to introduce Lenz's Law in greater detail also. So Faraday's Law and Lenz's Law should come together, but for now, we are going to focus more on Faraday's Law, and later we'll be moving on to Lenz law in the future recordings. Okay, so again, if we come back to our main concept of this chapter 5 says that the change of magnetic flux through a closed loop is going to induce an EMF and an induced current, an induced EMF and an induced current in the loop. So we have already studied what is magnetic flux already. Now we are going to study how does change of magnetic flux induce an EMF and a current. Okay, so the relationship between the change of magnetic flux and the EMF or the induced current can be described by Faraday's law and Lenz's law. So this is what we have discussed just now. Faraday's law together with Lenz's law explain the relationship between the change in magnetic flux through a closed loop and the EMF and current induced in the loop. So the change in magnetic flux will be the cause, and the EMF and the induced current will be the effect. Okay, because there is change of magnetic flux, therefore there is an induced EMF and an induced current in the loop. So that's the effect. Okay, so let's look at Faraday's law right now. So Faraday's law of induction says that the induced EMF in a closed loop, okay, which is epsilon EMF, okay, the induced EMF in a closed loop equals the negative of the time rate of change of the magnetic flux through the loop, equals to the negative of the time rate, that's why it's d over dt. D of what over dt is the d of the change of the magnetic flux through a loop, so that's phi. Okay, so it's d phi dt. Negative of d phi dt is equals to the EMF if it's a single loop. If your things has a loop but with multiple turns, then you have to change it to the magnetic flux linkage. But the magnetic flux linkage is just n times the magnetic flux. So since n, we never change the n usually. Okay, you can change the number of turns, but we really don't do that. So we can assume the n is constant and we bring it out from the differentiation. Okay, n is constant, therefore we bring it out. Okay, the negative over here is to indicate that the induced EMF or the induced current is always in the direction to oppose the change of magnetic flux, which is just Lenz's law. But well, the purpose of this sign over here later will help us to determine the direction of the induced EMF, will help us determine the direction of the induced current. And the induced EMF and the induced current should obey Lenz's law. So what is Lenz's law? Lenz's law says that the direction of any magnetic induction effect is such that to oppose the cause of the effect. So we learned just now that the effect is the induced EMF or the induced current, and the cause will be the change of magnetic flux. So you can change this sentence to become the direction of the induced EMF or the direction of the induced current or any kind of induction effect. We study a few. Okay, so the direction of this induced EMF or induced current is such that to oppose the cause of the effect. We learned that the cause is the change of magnetic flux. So the direction of the induced EMF or the direction of the induced current is to oppose the change of the magnetic flux. So later, when we talk about Lenz's law in the future recordings, we'll look at whether all this induced EMF or all this induced current is going to oppose the change of magnetic flux or not. If the magnetic flux is increasing, then induced EMF or induced current should be in the direction to reduce the magnetic flux. If the magnetic flux is reducing, then the induced EMF and the induced current will be in the direction to increase the magnetic flux. This is what we are going to investigate.